Hello and welcome to our lesson in physics. Our first unit in physics is on electrostatics, and the first conceptual topic that we come across when we look at Unit 1, electrostatics, is this idea of quantization of charge. What do we really mean by quantization of charge? That charge comes in definite quantities. Now, to understand this a little better, and because I understand this is a new concept to you, this whole idea of quantization is an absolutely brand new idea to you, let me elaborate this whole idea with simpler, familiar examples. So let's start off with this video that I prepared for you. Let's watch this video first, and towards the end of the video, we will be solving some numerical problems. So I suggest that you get your pen and paper and also take down notes as we proceed. Okay? The pace of the video, the pace of these lectures are going to be just right for you to be able to take these notes down and follow the class. If you're just going to listen, you might just miss out on a few things. So do take notes. So let's watch this video first. Let us look at quantization of charge and the idea behind the concept of quantization of charge. To understand that, let us consider these bricks. Of course, you know, we make walls with bricks. Let us assume we have these bricks which are, let's say, 20 centimeters in length. So if you take one brick, obviously the length is going to be just 20 centimeters with 240, with 360, with 480, and so on. So the length of the wall that you can make is going to be a multiple of the length of each brick. Of course, you must be thinking, what about the gaps over there? I'm just ignoring the gaps over there. We require to draw them just to show you the different bricks. And of course, in the practical situation, there would be a little bit of mortar going into that, and so the length of the wall would be slightly greater than that. We just ignore that for the moment. So, ignoring that, the length of the wall would be an integral multiple of the number of bricks. So if my wall had to be 80 centimeters long, well, I could make it just using 4 bricks. But if I had to make a wall 90 centimeters long, I either would have to take 4 bricks and make it 80 centimeters, or I would have to take 5 bricks, but which would make it 100 centimeters. Now the rule is that I am not allowed to break a brick and take a part of it. Either I use the whole brick or I don't use it at all. And using that premise, I will never be able to build a wall which is 90 centimeter long. Either it is going to be 80 centimeters or it is going to be 100 centimeters. Now let us carry this idea forward. If I take one single electron, then the charge on one single electron would be 1 into 1.6 10 to the power minus 19 Coulomb. If, however, I take 2, then the charge is going to be 3.2 into 10 to the power minus 19 Coulomb. If I take 3 electrons, then it's going to be 3 into 1.6 10 to the power minus 19, which is 4.8 into 10 to the power minus 19 Coulomb. And if I take 5, or rather 4, then it's going to be 6.4 into 10 to the power minus 19 Coulomb. And if I take 5, it's going to be 8 into 10 to the power minus 19 Coulomb. But remember, we cannot take half an electron. That is not possible. We cannot break an electron into 2 parts or whatever number of parts and take part of the charge. That we are not allowed to do. So either we take the whole electron or we don't take it at all. And therefore, if we take 1 electron, we get the charge 1.6 10 to the power minus 19 Coulomb. With 2, this much, 3.2 10 to the power minus 19, with 3, 4.8, with 4, 6.4. And so you can clearly see the values of charges lying between 1.6 10 to the power minus 19 and 3.2 10 to the power minus 19 Coulomb are not possible. There are a whole lot of values over here which are not possible. Similarly, between 3.2 and 4.8, those values are not possible. Because you're going to either take 2 electrons or you're going to take 3 electrons. You cannot take 2 and a fraction of an electron. Similarly, between 4.8 and 6.4, we cannot get these values. And so, charges jump over in steps. But of course, don't forget, there's a 10 to the power minus 19, so these steps are really small. But that is what we mean by the quantization of charge, that charge comes in definite quantities. So, let's look at this idea then. Therefore, we can write that the total charge on a body must be equal to an integer times the charge on an electron. Now, the plus or minus sign means if you're going to add electrons to the body, you would get negative charge. Whereas, if you take away electrons from the body, you would land up giving a positive charge to the body. And so, we write where Q is the total charge on the body, N is an integer like 1, 2, 3, etc. and E is the charge on an electron or proton. That proton got covered with my video. So that's a proton. And that is what would happen if you were taken away electrons from the body. Now that we understand this concept, let us try and do a few numericals, simple numericals. So let us see if it is possible to charge a body by 4.2 into 10 to the power minus 19 Coulomb. Let's try part A first. So we know that the total charge on a body is given by plus minus n times E, where n is the number of electrons to be extracted in this case because there is a plus sign over here. So we're going to take away electrons from the body, and E is the charge on an electron. So we put the values into the formula and look for n. How many electrons do we require? And it turns out that if you write an equation for n, it will be 4.2 10 to the power minus 19 divided by 1.6. This goes that side, and so the minus 19 cancels, and the decimal cancels, and you'll get left with 42 by 16, which is a fraction, 2.625, which means the number of electrons required is a fraction. Now, that is not possible. You cannot have fractional number of electrons. And therefore, it is not possible to charge a body by 4.2 into 10 to the power minus 19 Coulomb. Let's try another one. Part B is similar to part A, so you can do it on your own. I leave that to you. And let me do part C now. I mean, all of them are similar. I'm just looking for a different kind of an answer. So we start off at the same place, we put in the values like before in the equation, and we write an expression for n, and we do the same calculation. And this 10 to the power minus 19 this time goes up as plus 19, so plus 19 minus 15 will give you a plus 4, and you have a 42 by 16, which is 2.625 like before, and a 10 to the power 4, which means the decimal moves 4 places, and you get 26,250, which is not a fraction. And therefore, it is possible to charge a body by this quantity, 4.2 into 10 to the power minus 15 Coulomb. So you can now continue and finish parts D and part E. Well, that should solve your doubts about quantization of charge. Go through the video one more time if you still have any doubts, and see you then. Ciao. So there you are. We've looked at what we mean by quantization of charge. We've developed the numerical formula for it, Q equal to plus or minus n times E, where n is an integer and e is the charge on an electron or proton. And then we've solved these numerical problems, and I've left some of those numerical problems for you to solve. So make sure that you solve those numerical problems. Once we are through with this idea of quantization of charge, let's move forward. And our next topic here, one of the most important topics in this chapter on electrostatics, is Coulombs law. What is Coulombs law all about? Now, whenever we study physics, it's not enough to know that qualitatively charges repel or attract. Opposite charges attract, like charges repel. That's a qualitative knowledge. Physics always requires quantitative knowledge, and that's what Coulombs law does. Coulombs law gives us a formula, a working formula, with which we can move ahead and actually calculate how much force will be there between two known charges. So here I have another video for you. So let's have a look at this video, and then we'll move forward from that point onwards. Welcome to today's lesson. Today's lesson is on Coulombs law. So the question is, what is Coulombs law all about? Well, in physics, it is not enough to quantitatively know that like charges repel and unlike charges attract. We also need to know quantitatively the value of the force given to charges. Coulombs law gives us a mathematical expression using which we can calculate the value of the force. So let us consider 2-point charges, Q1 and Q2, placed a distance r apart. Well, in Coulombs law, the charges are considered to be point charges, and a little later I will explain to you what we mean by point charges. In this diagram, of course, the charges Q1 and Q2 do not look like point charges. Now, the beauty of Coulombs law is that whether the charges are positive or negative, meaning to say both positive or both negative, or one positive, one negative, the value, or rather the structure of the expression, remains the same. The value of the force remains the same. Only if both are positive or both are negative, it is a repulsive force, and if one is positive and one is negative, it is an attractive force. Coulombs law states that the magnitude of the force F between two charges is, firstly, directly proportional to the product of the absolute values of the charges Q1 and Q2, and inversely proportional to the square of the distance r between them. Certainly, you would be able to guess that the magnitude of the force would depend on the intervening medium, that is, the medium between the two charges, meaning to say whether the charges are placed in air or underwater, or there is some other medium between them. So mathematically, if we are to express Coulombs law, then we may write the force of attraction or repulsion between 2-point charges is directly proportional to the product of the absolute values of the two charges, Q1 and Q2. It is inversely proportional to the square of the distance r between the two charges. And so combining the two terms, we may write F is proportional to Q1 into Q2 by R square, or we may write F is equal to K Q1 Q2 by R square, where K is a constant of proportionality whose value depends on the nature of the intervening medium as also on the system of units we are choosing. At this point of time, I want you to compare Coulombs law expression to the expression that you learnt in class 11 on Newton's law of gravitation. Look at the structure of the two expressions. They are absolutely similar. It is a constant times Q1 Q2 by R square. This is a constant times M1 M2 by R square. Now, there's a little exercise that I want you to do a little later, but I'll tell you that a little later. But just for now, look at the similarity of the expressions. Let's move forward. In the SI system of units, if the intervening medium is air or vacuum, then K is equal to 1 by 4 pi epsilon naught. That's the shape that K takes, where epsilon naught is the permittivity of free space and its value is 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. And K, the whole thing, 1 by 4 pi epsilon naught, that is K, turns out to be 9 into 10 to the power 9 Newton meter square per Coulomb square. So we may write the complete expression as F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. And we will be using epsilon naught as long as the intervening medium is air or vacuum. And because we are working in the SI system of units, and this is a force, the answer you will get will be in Newton. The SI unit of force is in Newton. So that is Coulombs law. But this formula only gives you the magnitude of the force. Remember, we must understand that if the two charges are the same sign, both positive or both negative, then the force will be repulsive. That is, the two charges will tend to move away from each other. And if the two charges have opposite signs, then there will be attraction. That is, the two charges will tend to move towards each other. And so, because direction is involved in any force, we must be able to write the vector form of this equation. We will take that up in the next lesson. But before we go to the next lesson and we wind up this lesson, I want you to do a little bit of small homework. Look at the value of the constant K, which is 9 into 10 to the power 9. Just look at the magnitude. Forget the units for the moment. Just look at the magnitude. 9 into 10 to the power 9. And recall the value of capital G, the universal gravitational constant that we came across in the chapter on Newton's law of gravitation. Compare the two values, the values of capital G and K here. And that will give you an idea of how much stronger this force of attraction or repulsion between two charges is in comparison to the force of gravitation. But really, before I actually wind up this chapter, or rather this topic on Coulombs law, there are 2 or 3 things that I really want to discuss, because these are very, very often asked by students. The first thing that students ask is, why is Coulombs law an inverse square law? Why isn't it, let's say, a 1 by r law or a 1 by r cubed law for that matter? Why is it a 1 by r square law? Now, to understand that, let us recall the fact that the surface area of a sphere is 4 pi r square. This you've learned earlier. Now, let's come to this diagram. Here, imagine this is the center of a sphere, and I have a source of light over here. And at a distance r from the source of light, the area subtended is A. And at a distance 2r, the surface area would be 4 pi into 2r square, which would be 4r square. And so here you can see the area becomes 4 times 1, 2, 3, 4 times the area here. Similarly, if the radius is 3r, that means I am 3 times as far away from the source as this, then it becomes 3r whole thing square, and which is 9r square, which means 9 times r square, which is this case. And therefore you can see there are 9 of these over here. Now, that must be just simple mathematics. What is the implication of this? Look at this. The amount of light incident on this area through this solid angle, if we say that is, let's say, an amount I, then that same amount of light is now incident on 4 times the area. And here, that same amount of light is incident on an area which is 9 times this area. And therefore, the amount of light incident on area A here will be 1/9 that of this. And the amount of light incident on A here would be 1/4 of this. And so clearly you can see that as the distance increases, the amount of light incident on equal area falls off as the square of the distance. Here it is 1/9, here it is 1/4, and so this distance was 3 times and this distance was 2 times. So 1 by 2 squared, 1 by 3 squared. And that is exactly the idea in Coulombs law as well. Imagine that this is a charge, and the charge is producing its field, and we are measuring the force experienced by a charge Q placed here, and let's say that force experienced is F. Then the force experienced over here would be F by 4, and the force experienced over here would be F by 9 by the same logic. Because what we say is electric charge, or rather electrostatic field, is isotropic. Now what does that mean? Well, it means that electrostatic field has no preference of direction. It means it acts equally in all directions. It means that the electric field does not have any preference of direction, and so the electric field of a positive point charge will be like a sphere emanating outwards from the point charge, keeping the point charge at the center. So if you can imagine a sphere with the charge at the center and having a radius r, then it has a certain surface area. Now imagine another sphere with radius 2r. So that will be a larger surface area, an outer shell. But the same amount of electric field is now spread out over a larger surface, and therefore the effect on the same amount of area, just like here, is going to be 1/4 that in this case. So that should explain and clarify why Coulombs law is an inverse square law. The idea is that the electrostatic field is isotropic, and as I said, it means that the electric field acts equally in all directions. It has no preference of direction. So if field spreads out equally in all directions, then it gets equally divided as the area increases. That is the idea. Now there are 2 more things that I would like to mention before I actually close this topic. The first thing is, when we talk of 2-point charges in Coulombs law, And in this diagram, these two charges are both positive, Q1 and Q2 are both positive, and therefore the force between them would be repulsive. These forces act along the line joining the two charges. If it was attractive, if one was positive and the other was negative, then the forces would be in this direction and this direction, but still they would act along the line joining the two charges. And such forces are said to be central forces. So, Coulomb force or electrostatic force is a central force. And the last thing that I want to mention before I actually wind up this topic is that electrostatic force is also a conservative force. I'll just leave it there and I will not explain to you what a conservative force is, because we will have a whole section on that later on, a small section, but we will have it elaborately later on. So for the moment, just remember these two properties, that Coulomb force is a central force as well as Coulomb force is a conservative force. So that's it then. Study hard. Ciao.